So today we'll be talking about the pumping lemma. And the pumping lemma is a lemma that can be used to prove that certain languages are non-regular. What does non-regular mean? That it cannot be recognized by a DFA or an NFA or a regular expression. So examples of non-regular languages are the language L, 0n, 1n, n greater than or equal to 0. So this language cannot be recognized using a finite automaton or a regular expression. Intuitively, the reason for this, intuitively, is that the DFA will have to count the number of zeros, and it will have to count the number of ones, and check that the number of zeros is equal to the number of ones. Now, in order to count an arbitrary number of zeros, so this should be a string. This should be true for an arbitrary value of n. So, building an NFA or a DFA for a specific value of n is trivial. It's like this language, L2, 0, 100, 1, 100. This is trivial. Why?
Does he have a finite?
It's what?
It's finite.
Yeah, it's finite. In fact, there is only a single string. There is only a single string. So this is, in fact, this is a valid, this by itself is a valid regular expression for this language. Or to find a DFA or an NFA, then you can do just 100 zeros with an NFA. You have, up to 100 zeros, and then 100 ones. So that's trivial. You just put 100 zeros and 100 ones, and that will recognize this for a specific value of n. For a constant value of n, this is trivial. The language is definitely regular because it will have only a single string in it. But for an arbitrary value of n, how do you know how many states you will need? It's an arbitrary value of n, so you cannot do it with a finite number of states. This is the intuition. Now, this is something that we will formalize later, this lecture. Another example of a non-regular language is the language L, WW, such that W belongs to sigma star. How would you describe this language? A language in which each string consists of two identical halves. It's like this string, 1010, belongs to this language. 101, 101 belongs to this language. 110, 110 belongs to this language. So a string that you can split into two identicals. So this is W and this is W. This is W and this is W. Again, thinking about this, again, this is something that you cannot do with a DFA, because the DFA will have to check the first half, or it will have to recognize it, and then it will have to check that the second half is identical to the first half, and for an arbitrarily long half. So this W is arbitrarily long. So again, this is something that you cannot do with a finite automaton. Now, the pumping lemma formalizes this intuition by giving a certain property of regular languages, a property that all regular languages must satisfy. And then, if you argue that some language does not satisfy this property, then you prove that this language is non-regular. So what's that property? The property is the following. So now if you have now suppose that you have a DFA or an NFA with 10 states. And this DFA with 10 states processes a string with 10 symbols. So you will have, well, let's draw the string first. So the string is, symbol 1, symbol 2, symbol 3 through symbol 10. Now, the idea is that with this string, you start with the start state Q0. Then the first symbol is going to put you in some other state, maybe Q5. The second symbol is going to put you in some other state, maybe Q7. And this will put you in another state like maybe Q2. And finally, this will put you in some accept state. Maybe Q4 is an accept state, if this string belongs to the length. Now, how many states will you have here? What's the total number of states in this path? Is it 10 or 11?
You start with,
So is it 10 or 11? Okay, so when you do this, so this is a string with 2 symbols. This is Q0, Q1, Q2. How many states do we need to process a string with 2
that
symbols?
would be 3, so that would be 11.
Yeah. So here we will need 11 states. There will definitely be 11 states. Okay. So now with 11 states, and the DFA has 10 states. So what does this tell you about these states here that you go through to process this string that has 10 symbols in it?
That it reuses the state?
That you see what?
It reuses one of the state?
Exactly. Yeah. So this is the key idea. That to process a string with length 10 or greater, you must repeat states. You don't have enough states. Assuming that the DFA has 10 states in it, there will be some repeated states. And of course, if you have a string that is longer than 10, you'll have even, or you may have even more repetition. You will repeat more states. So now let's generalize this. Suppose that I have a DFA with P states in general that processes a string with P symbols. Okay. So now this is no longer 10. This is SP. And then I will end up with some accept state here, whatever that state is, maybe Q917 or something. Now, since I must repeat states, at some point there has to be a repeated section. So some state, at least one state must appear twice. So let's assume that this state is, well, let's call it QR for repeat. And then QR must appear again. With this length of the string, some state must repeat. And let's call this QR. Now between these two QRs, we will have at least one symbol, one or more symbols. To go from one state to another, you need at least one symbol. So you have here, you'll have a substring that has at least one symbol in it. Now, well, this part here, this part that takes you from QR to QR again, because you must repeat. Now let's call it Y. And let's call this section X. And this section Z. So now we are dividing this string into 3 pieces. The piece that repeats, now we know that something will have to repeat. The piece that takes you from QR to QR. And then we will call whatever comes before this X, and we will call whatever comes after it Z. Now, what if I tell you that, now this string that we are processing is the string S equals X, Y, Z. Now, what about the string S equals X, Y, Y, Z? Will this string necessarily belong to the language or not? Yes, it will. It will certainly belong to the language. Why? Who can give me a clear argument why the string X, Y, Y, Z must belong to the language? Yes.
Since it's already repeating, it could repeat again in the midst of it.
Okay, so it could repeat again. So here we have a Y. What if we get another Y? You know, this other Y here will take us to another QR. So basically from QR, if you are in QR and you get a Y, you know, this Y is not necessarily one symbol. It's a substring. It can have one or more symbols in it. But if you get this sequence of symbols, this Y sequence, one or more symbols, if you are in R and you get this, it will always take you to an R, a QR. And now if this Y takes you to QR, then you know that after QR, there is a path to an accept state. So no matter how many times you repeat this, you will get a string that belongs to the language. So I know that X, Y, Y, Z belongs to the language, and I know that X, Y, 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 Z belongs to the language, and I know that in general, X, Y, repeated I times Z belongs to the language, where I is what?
An integer?
Yeah, it can be anything. What about I equals 0? Will I equals 0 give me a string that belongs to the language?
Yeah.
Why?
Because you're already at QR, so if you get a Z after that, it'll go to the accept.
Exactly. So if you are here and you don't even put a Y, right? So you will, if you get a Z after this, so the Z takes you from QR to Q17. If you are already in QR, and if you get a Z without getting a Y, then you will get a string that belongs to the language. So in fact, this is good. This is true for any I that is greater than or equal to 0. Okay. So now, this is the idea. What does this tell us? It tells us that for any regular language, if the language is regular, then there has to be a piece that can be repeated. And you can repeat this piece as many times as you want, and you will still get strings that belong to the language. Now the idea of the pumping lemma, or the way the pumping lemma is used to prove that certain languages are not regular, is by showing that for some languages, if you use that piece to repeat, or if you repeat that piece and you get other strings, you will necessarily get a string that does not belong to the language. Okay, we'll show this by example. But let's first state the pumping lemma. So the pumping lemma if A is a regular language, then or there exists a certain length P called the pumping length. So this pumping length for us is the pumping length is just the number of states in a DFA that recognizes this language. The number of states in a DFA that recognizes this language. But as we have seen in previous lectures, there can be multiple DFAs that recognize the same language, and they can have different lengths. So this should be true for any length of any DFA that recognizes the language. There exists a certain length P such that every string S that belongs to A of length greater than or equal to P, can be divided such that every string can be divided into 3 pieces. So S equals X, Y, Z that satisfy the following conditions. Satisfy the following conditions. And these conditions are, condition number 1, X, Y, I, Z belongs to the language for every I greater than or equal to 0. And the part that we repeat, which is the Y, so this notation means the length of Y. So this Y means length of Y. It's like the magnitude of Y. Length of Y must be greater than or equal to 1. So there has to be that repeatable piece cannot be the null string. It has to be, it has to have at least one symbol in it. And XY is less than or equal to P. Now what does the third condition tell us? What does this mean? The length of XY is less than or equal to P. What does this tell us? So here, we looked at a string of length P, and we said that with length P, you must have a repeating part that appears before P, or within the first P symbols. You must have a repeating part. So the Y, that repeatable piece, or pumpable piece, must appear within the first P symbols. That's the idea. Okay, so the idea is that with this P, you will need P plus 1 states, so you must repeat a state, which means that that this string must have that repeatable piece. By the way, this argument that with P plus 1 states and the finite automaton has only P distinct states, that's what we call a pigeonhole, the pigeonhole principle. Yeah. Well, have you seen the pigeonhole principle in discrete math? Yeah. So the pigeonhole principle is you have this string that requires P plus 1 states, but the finite automaton has only P states. This means that one state must repeat. At least one state must repeat. Okay. Now, so this is the statement of the pumping lemma. Now let's see how we can use it to prove that certain languages are not regular.
There's just 3 conditions, right?
Yes, there are only 3 conditions. Yes. Okay, so use the pumping lemma to prove that L equals 0n, 1n for any n greater than or equal to 0 is non-regular. So the idea is to use a proof by contradiction. So we will assume that it's regular, and then we will reach a contradiction. So it's a proof by contradiction. So by contradiction, assume that L is regular. If L is regular, then it satisfies the three conditions in the pumping lemma. Now, how do we use this to prove that this is not regular? We find a string that is sufficiently long to show that if I use the pumping lemma, I'm going to be putting this DFA that you may try to construct to recognize this language is going to accept strings that do not belong to the language. So consider the string zero P, 1P. So where did I come up with this string? Well, it's a string that is designed to basically show that this language will not satisfy the conditions in the pumping lemma. Now, how do you figure out, how do you figure out a good string for proving that a certain language is non-regular? So this is something that you will learn by practice. So this is, coming up with the right string requires some creativity. And for now, this is the string that people have come up with, a string that people have come up with a long time ago to show that this language is non-regular. Now, why does this string show that this language is non-regular? Now, this is 0P, 1P. So you have P0s followed by P1s. So this is going to be like this. 0, 0, 0, 0, up to P, and then P plus 1 up to 2P, 1, 1, 1, 1. And this is 0. Now, what does the pumping lemma tell you? The pumping lemma tells you that there has to be some repeated state here, or there has to be a repeatable piece, Y. And this Y must appear in less than or equal P. So this Y must appear somewhere here, before P plus 1. So there is a Y that you can repeat, somewhere before P plus 1. Within the first P symbols, there is a Y that you can repeat. Now, if you repeat this Y, like if you look at the string X, Y, Y, Z, and this Y, the size of Y is greater than or equal to 1. So if you repeat this X, Y, Y, Z, or if you look at X, Y, Y, Z, will this belong to the language? Can this belong to the language? So here you have P1s and here you have P0s. So if you pump this Y, if you repeat this Y, how many zeros will you get?
More than P.
More than P. So if you repeat this twice, you will get more than P zeros. In fact, if you repeat the Y 0 times, you will get less than 0. You'll get less than P zeros. So only for Y equals 1, the string belongs to the language. For Y equals 0, it will have fewer zeros than 1s. For Y equals 2 or greater, it will have more zeros than 1s. So this is here, by doing this, we are reaching a contradiction. We are saying that if we assume that this language is regular, this language will not satisfy the pumping lemma because this string here does not belong to the language. So if we satisfy conditions 2 and 3, we will get a string X, Y, Y, Z that does not belong to the language, or X, Y, 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 Z. Do you see the point here? So the point is that, the pumping lemma is saying that with a finite number of states, you must repeat a piece. There is a piece in every string with length p or greater. Every string with p of length p or greater, there is that repeatable piece. And that repeatable piece, for some string, for certain kinds of strings, or for certain kinds of languages, that repeatable string, if you repeat it, you will get a string that does not belong to the language. Like this. If you repeat this Y, you will get more zeros than ones. Or if you skip the Y completely, you will get fewer zeros than ones. So this is the idea. While for regular languages, you can always find a repeatable piece and repeat it, and you get strings that belong to the language. Okay. Any questions on this? So let me write this down. Consider the string 0p01. Now, because xy is less than or equal p, y must consist totally or of zeros. Must consist of only zeros. Or the y must be within the first p symbols of the string, then y must consist of only zeros. Now, the string x, y, I, z for I greater than or equal to 2 will have more zeros than ones. Okay, the string x, y, I, z for I greater than or equal to 2 will have more than zeros than ones. Therefore, it does not belong to L, which is a contradiction. It failed to satisfy the properties of this property of regular languages. So L must be non-regular. Now, maybe to convince you, that we can always use this argument. We can apply, use this argument to prove that certain languages are not regular, and we cannot use it to prove that regular languages are non-regular. So let's look at some of the regular languages that we have learned. So, for example, what are the regular languages that we have looked at? We have looked at language, L, W such that W starts with 1. I mean, this is easily a regular language, and even if there is a repeatable piece, you can repeat that piece, whatever that piece is, and still get a string that belongs to the language. So you have this string that starts with 1, and then followed by whatever, S2, S3, S4, all the way to SP. Whatever that repeatable piece is, there is some repeatable piece here. Whatever you repeat, you still get a string that starts with 1. So clearly, this is a very easy language to recognize. You just look at the first symbol, and if it satisfies this, repeat this as many times as you want, and you still get a string that belongs to the language. How about the language, a little bit more complicated language, which is W contains 101 as a substring. Again, in this case, you'll have S1, S2, and then at some point you'll have 101, and then S whatever number, S19, S20, SP. Now, every string will contain this substring. Now, again, for this language, if P is large enough, if the language has enough states, you will always find a repeatable part. Like, you can find a Y here, or a Y here. A Y that doesn't overlap with this substring that you are trying to recognize. And then if you repeat anything here, you still get a string that belongs to the language. So you repeat this 1,000 times, or as many times as you want, you still get a string that belongs to the language. Repeat this, you will get a string that belongs to the language. So with this, the nature of this language is that whether a string belongs to the language or not does not have to consider an arbitrarily long string, or if the property is satisfied at some point, right? You can't break this by repeating pieces that appear before P. Okay. Let's look at the language. W L equals W such that W has an odd number of ones. Odd number of ones. Yes.
So if Y is in both positions, is it in both at the same time, or do you choose where to put it?
No, there is a Y. There is a repeatable Y. So it can be here or here.
But it's not in both at the same time?
Yeah, not in both. It's either this or this. Okay. So there is only one Y to repeat. Okay. So now W has an odd number of ones. You have a string with an odd number of ones. So suppose that you have a string with an odd number of ones, S1, S2, S3 through SP, and okay. So can you find with an odd number of ones, there will be some repeated state. So here, QR, and this is a QR. And this is the piece that you repeat, which is the Y. Okay, so now, in a string that satisfies this property, has an odd number of Ys, odd number of ones, you can always find a piece that you can safely repeat as many times as you want, and it will still produce a string that belongs to the language, basically without having to check what comes after this Y. So what should this Y, what should be the property of this Y here? Of this repeatable piece, a valid repeatable piece for this language?
I would guess this is zeros and ones, so it would be zeros.
Not necessarily. It can have zeros or ones.
I could also, with an odd number, so the...
No, it cannot be an odd number. What number of ones will not change the property? What should the number of ones be for Y? What should the number of ones in Y be in order to preserve the property of the language?
An even number of ones.
Yes. An even number of ones in Y will always preserve the property of the language because it does not change whether the number of ones is odd or even. So if I tell you that one has 6 ones in it, I don't care how many ones I have here or there. This will present, if you repeat this, if you repeat an even number of ones, you will always preserve the property of the language, because all what you care about is odd. So if it has an odd number of ones, and you add an even number of ones to it, you still have an odd number of ones. So odd plus even is odd, and even plus even is even. So adding even will always preserve the property of the language, whether it's odd or even. So I'm trying to convince you here that with the regular languages that we have been able to recognize using finite automata, it will always be okay. You can always find a repeatable piece, and you can repeat it as many times as you want and still preserve the property of the language. But we fail to do this with 0n, 1n. Why? Because the repeatable part must be here, and by repeating something here, we will violate the property of the language, because the number of zeros will no longer be equal to the number of ones, or because there is a property, because we have to count the number of ones, because to satisfy the property of the language, we'll have to look at the entire string, and whatever change we make in this part can violate the property of the language. In this case, it will increase the number of zeros.